Hi, welcome back to chemistry. This is Miss Gray, and we're working on the final podcast of Unit 5, Metallic Bonding. So I've got a picture here for you. What I've shown here in this picture is a whole bunch of metal atoms. You see, what happens with metal atoms is that they've got these positively charged nuclei, and then surrounding them, valence electrons. And the valence electrons, of course, are the ones on the very outside ring. They're not the last electrons to fill in, since those would go into 3d, 4d, or 5d, sometimes even f orbitals. But they are the electrons that are filling in the s orbital, right? Because it's higher energy, so those are the ones that are the valence electrons. And then we have cations, or positively charged ions, that make up the nucleus. So these valence electrons stick to the cations because of the opposite charge, right? A negative is attracted to a positive, so they hang around each other. These electrons don't know the difference between this positive charge and this positive charge. And in metal ions, they're free to move around. So the electrons in metal atoms move freely from one nucleus to the other. The valence electrons don't really get stuck. The core electrons pretty much stay put, but these valence electrons, they're free to move about and create what we call a sea of mobile electrons surrounding the nuclei that stay locked into place in their crystal structure. So that's going to be important in understanding the properties of metals. You see, since these nuclei are stuck, but the electrons are not, then shifting the nuclei doesn't break the entire crystal. It just allows the electrons to squish around a little bit. You know, it's a sea of electrons, and so they're squishy. They can move around a little bit and accommodate some malleability or ductility in that metal. So let's see what happens when two metals come together. We make alloys. When we make alloys of metals, then basically what we're saying is we're mixing two metals, but because their electrons are free to move around the entire structure, then they're not locked into place, and it creates what's called a metallic bond. Metallic bonds form when the electrons delocalize. So interstitial alloys are like steel, where smaller atoms fit in between the holes in the larger atoms that they're embedded in. So suppose that these large atoms here represent atoms of iron. And if these are atoms of iron, then we could make steel stronger by placing small carbon atoms in between the little holes or the gaps left when we stack the iron atoms close together. When we do that, then we provide rigidity and strength to the entire structure, so that now we have a metal that's stronger than iron itself could have been. And it's much stronger than what carbon would be by itself. So this carbonized or anodized steel is going to be stronger. The percent of carbon is going to determine the strength. So if you needed something flexible, you might have a low percent of carbon, like less than 1%. But if you needed really strong, rigid steel, like in a railroad track, then you might want up to even 6% of that steel to be made of carbon, to add a lot of strength to the entire structure. Now let's look at a different kind of alloy, the substitutional alloy. In a substitutional alloy, that's where we would take our atoms of one metal and in place of them put something different. So this is what happens with brass. We would take the copper atoms and replace them with zinc. So if these are coppers, we can replace the copper with the zinc and we make brass. So the brass to copper ratios may vary, but for standard types of brass, there's a standard composition of the ratio of copper to zinc. That's what a substitutional alloy is. And that's it for metallic bonding. So I want to talk to you about your lab. You're going to be making some metal alloys in your lab, the alchemist's dream, also known as the penny lab. So here's your first warning. Bring your own pennies. You need 3 pennies. If you have to buy my pennies, It's going to cost you $1 for 3 pennies. If you think that's a ripoff, you should see what I have to pay for taxes. Second pre-lab precaution, wear long sleeves. The sodium hydroxide in this lab is an irritant, and if it gets on your skin, then it might itch your skin, and if you scratch the itch, you'll work it into your bloodstream, and it could be really dangerous. So wear long sleeves to do this lab, and by all means, if you feel itchy, go rinse your skin off with water, don't scratch, okay? And then finally, you need to understand powdered zinc cannot come into contact with water or with the damp paper towels that you're using to clean up the mess of your lab. So do not put powdered zinc into my trash can where damp paper towels are. Make sure that you check with your teacher so that you know exactly what to do with any waste from this lab. We don't want to make fires in the trash can. That would be embarrassing. All right, so we want to keep you guys safe, but this is a really fun lab. So bring your pennies, bring your worksheet so that you can fill in your information for the lab, and wear long sleeves. See you in class.